Have you ever been using a piece of software and suddenly it throws some generic error or maybe it crashes and you just wish you could freeze time?
Right.
To look inside the machine, do a bit of digital forensics, and understand not just what happened, but the microscopic why in that moment before it failed.
That exact ability to halt a program right in the middle of its execution and just inspect the complete machine state, that's the fundamental superpower of software security analysis.
And that's what we're talking about today. We're giving you a quick foundational path to gaining that power. Our deep dive is focused on the GNU debugger, GDB, and a really powerful enhancement layer that turns it into a specialized security tool.
Yep, EP.
So our mission is to unpack these tools, moving you from a basic understanding of how code runs to knowing exactly how professionals analyze system state for forensics and exploit development.
Let's start with the absolute foundation then. GDB is, well, it's essentially a forensic laboratory for running software.
A forensic lab. I like that.
Yeah, it lets you see what's going on inside another program while it's running, or, and this is the critical part, it lets you inspect the program's state, the memory, the registers, the specific instruction at the precise moment it crashed.
Now, a quick note on setup, because this is super important for anyone wanting to follow along.
Oh yeah, this is crucial.
If you plan on using PEDA, which we definitely recommend, you need to make sure you're running GDB version 13.1 or older. There's some compatibility things there.
And just as critically, GDB needs context to work with. So you have to compile the program you want to debug with the G switch.
Right, the debug flag.
Exactly. That switch tells the compiler to include all the symbolic information, like your variable names and line numbers. So GDB isn't just, flying blind.
Okay, so once that's ready, we're in. The startup command is gdb-q.output program. The dju just gets you to the command line without all the startup text.
Right, cuts out the noise. And our reference material uses a classic C++ Stack Overflow demo, which is just the perfect test case for these tools.
It really is.
So, moving into execution. The first thing GDB gives you is the ability to reconstruct the crime scene. You use the run command.
And you're not just starting a program, right?
Not at all. You're setting up a virtual forensic lab around it. You can even pass arguments or redirect input from a file like run args input.txt.
And if you need to start over?
Simple. The kill command just terminates the program running inside the debugger, and you can reset your investigation.
But what if I need to stop execution halfway through, say, a massive loop or inside a function, I think is the problem. I mean, we can't step through thousands of lines of code by hand.
Exactly. And that's why breakpoints are so critical. They let you define specific spots where GDB will just automatically halt execution.
So you set them with break or just B?
Yep, B for short. You can specify a line number, a function name, even a raw memory address.
And once you hit one, you inspect everything and then you use continue or C to just let it run until the next breakpoint.
That's the flow.
Okay, so we've stopped the program. The next layer of control is stepping. For anyone learning this, knowing the difference between statement level and instruction level stepping is, well, it's key.
It's a huge time saver.
At the high level, the source code level, you have step, or S. That means you step into a function call you've reached.
And on the flip side, you have next, or N. That command executes the entire function call in one go, stepping over it.
Which is great when you're debugging your own code and you just, the library function you're calling is solid. You don't need to inspect it.
Saves a massive amount of time, absolutely.
But the really cool part, for me anyway, is when you switch to instruction stepping. And we want to see the raw machine code, the assembly.
Now you're getting deep.
Yeah.
For that, we switch to steppy, or C. This moves you forward by one single machine instruction.
One instruction at a time.
And its partner command is nextTie, or NIE. It also steps one instruction, but it cleverly skips over any function calls at the assembly level.
Which is vital when you're focused purely on the assembly flow in the current function and you don't want to get sidetracked into some library call.
Precisely.
So once we've used those breakpoints to halt the program, the next logical step is to stop looking at the high-level code and start looking at those raw instructions.
And for that, you use the disassemble command, followed by the function name you're interested in.
Right. And when you do that, you'll probably see the output in the default, what is it, AT&T syntax?
It is, yeah. And for a lot of people, that can be a bit harder to read. The source and destination can feel backward.
So a pro tip is to issue the command, set disassembly flavor intel.
Always. It just changes how you mentally process the code, makes the source and destination operands much, much clearer.
Beyond the instructions, GDB is also our window into the data itself. You can do basic math right in the prompt, like print 2 plus 2.
Or, more usefully, examine registers combined with arithmetic, something like print tep plus 4. You can check a variable by name, or a register directly with print fpip.
What's really fascinating here, though, is the flexibility of that print command when you use the format flags, the format syntax.
Oh, yeah. This is where you go from being a novice to a power user. You gain control over how GDB interprets the data it's showing you.
Exactly. You're not just stuck with the default hex output. If you want to see that same memory value as a signed decimal, you use PD.
Or if you're looking at flags and need to see the raw bits, PT gives you the binary format.
And for character arrays, obviously PS to see it as a string, being able to just instantly flip between these formats makes bug hunting so much faster.
But the ultimate command for memory inspection, the one that's essential for security research, is the standalone X command.
Examine memory.
Exactly. This is how you look at raw memory directly. The syntax looks a bit complex at first, but every part has a purpose. X count size format register memory.
Okay, let's break that down. The format part dictates how the data is displayed.
Huh.
O for octal, X for hex, T for binary.
And the size tells GDB what size chunks to read. You have B for a single byte, H for a half word, so 2 bytes.
And W for a word, which is 4 bytes. And that's usually the default, right?
It is on most 32-bit systems because it matches the size of a memory address or a pointer. And that is the crucial link.
So if we're hunting a buffer overflow, we aren't just looking at random bytes, we're specifically looking at those 4-byte chunks, those pointers.
You got it. And the count is just how many of those chunks you want to see.
The example in the source material really puts this all together perfectly. It's by 40W a cas esp.
Yeah, that command is a classic.
So what is that telling GDB to do exactly?
Okay, so that command translates to, starting from the current top of the stack, which is pointed to by the esp register, show me 40 chunks of memory.
And the W and the X?
The W says treat each chunk as a 4-byte word, and the X says show me the contents in hexadecimal format.
And because stack pointers and return addresses are typically 4 bytes long, looking at memory this way lets you visually trace how data, and maybe a potential exploit, is flowing onto the stack.
That structural insight is what turns basic debugging into real security analysis.
Okay, so we've covered the fundamentals of GDB. Now let's talk about optimizing that whole process for writing exploits. We're moving on to PEDA.
The Python Exploit Development Assistance Layer.
Right. And PEDA is an enhancement. It's not a replacement.
That's a key point. It takes the power of GDB and just focuses it for security analysis. All those commands we just learned, run, break, print, they all still work perfectly inside PEDA.
The main problem PEDA solves is information overload. In vanilla GDB, when you hit a breakpoint, you just get a simple prompt.
It's pretty Spartan, yeah.
In PEDA, you immediately get these specialized context views that show you the most important pieces of data right away.
Exactly. When you hit a breakpoint, you don't have to manually type commands to inspect registers. The context reg view is right there, showing you the current state of all the registers and flags.
And there's context code.
Which shows you the disassembly right around your current instruction pointer.
And most importantly, for a Stack Overflow demo, there's context stack. It immediately shows you the stack without you needing to type that complex by 40WXS command every single time.
It's a massive speed up for vulnerability hunting.
PEDA also gives you this immediate intelligence on your target program. You can quickly check its security settings.
Right. You can see if standard protections like ASLR address, space layout randomization, or the NX bit are enabled.
And knowing that is just... It's crucial. That intelligence tells you right away if you need to plan for more advanced attacks, like using ROP, return-oriented programming.
It informs your entire strategy before you've even tried to launch a payload.
Speaking of strategy, PEDA's functions for buffer overflow analysis are, well, they're game changers.
Absolutely. The first step in that workflow is pattern generation. PEDA helps you create these mathematically predictable strings, patterns.
And these patterns aren't just random junk data.
Not at all. They're designed so that when the program crashes and overwrites the return address, that overwritten value is guaranteed to be unique and mathematically traceable.
This is where the magic happens.
It really is, because then you use PATS or pattern search. After the program crashes with that pattern, you don't have to manually count bytes.
Which is a nightmare.
A total nightmare. Instead, this command looks at the specific junk value that ended up in the EIP register. It searches for that value in the pattern you generated. And it automatically calculates the EIP offset.
And that offset the exact number of bytes of junk you need before you can start overwriting the return address. That is the golden ticket for a buffer overflow exploit.
And PEDA gives it to you instantly. It saves hours of manual accounting and just frustration.
And finally, PEDA even streamlines the last step, shellcode generation.
Yep. It has a built-in capability to generate executable payloads. The source mentions shellcode generate by 86 Linux exec as an example.
So the entire analysis, from finding the crash to building the exploit payload, it's all integrated into one environment.
That's the goal.
So let's just step back and summarize what this all means for you, the listener. We started with GDB, which gives us that foundational ability to stop execution, step through code instruction by instruction, and inspect memory with surgical precision.
Thanks to commands like X and those flexible print formats.
And then we brought in PEDA, which takes that surgical precision and optimizes it for vulnerability research.
It does that by giving you those immediate contextual views of registers, code, and the stack, and then specialized tools like pattern search. It turns GDB into the definitive environment for finding those machine state failure points.
This whole process moves you beyond just seeing a program crash with some generic error message to understanding the precise machine state, the register values, the stack contents, the specific instructions that led to that failure.
And that deeper architectural level of understanding is the very foundation for analyzing sophisticated bugs or, developing effective security countermeasures.
For those of you who are now hungry for more, the ability to control execution and data flow we talked about today, it links directly to advanced exploit development.
You should definitely explore the supplementary resources on exploit writing using Python, tools that build on these very debugging principles.
And for anyone who loves complexity, look into advanced concepts like ROP, return-oriented programming, and ROP gadgets.
Right. Those techniques become necessary when security defenses like NX are enabled, and they build directly upon the ability to precisely control program flow that you learn with GDB and PEDA.
So this all raises an important question for you to think about as you wrap up this deep dive.
If tools like PEDA make it this straightforward to identify and pinpoint the exact memory offset needed to compromise a program, effectively streamlining an attacker's job, what specific architectural or operating system defenses do developers really need to prioritize to make a successful exploit non-trivial again?
That's something to mull over as you begin to explore inside the machine yourself. Until our next deep dive, keep digging.